Hey guys, welcome to All Electronics. In this video, we are talking about noise. What is noise temperature? Why is really important to think about noise when we are designing receivers? And in the end of the video, we are going to understand how noise temperatures relate to noise figures and what a noise figure really is. It's a pleasure to meet you here on All Electronics. My name is Gregory. Prepare your coffee and come with me. Well guys, in this video my idea is to talk about noise and noise temperatures, but not going to the math, because the mathematics about noise are readily available on the internet. What I think is more important is for us to grab the real understanding of why it's important to think about noise when we are talking about receivers. How the signal-to-noise ratio is degraded in an amplifier chain, how it relates to noise temperatures, and what is the difference between a noise temperature and a noise figure. We can draw a very simplified receiver, like an antenna going to an amplifier, going to a bandpass filter. We are going to understand later why it's important to always draw the bandpass filter in here, demonstrating that we are thinking on the receiver chain with the knowledge of the receiver bandwidth, thinking about the bandwidth of the receiver. And here we have the signal amplified, recovered from the antenna and amplified, so it can be used by the rest of the receiver. The demodulation chain, the IF section, the modulation chain, the SP, all the other parts of the receiver. The antenna is receiving the signal from the air, and the antenna is also capturing noise. And we're gonna consider that these noises here are not other signals. These noise here are thermal noise that the antenna is seeing, thermal noise that the antenna is receiving. So the antenna captures the signal plus the noise. Okay, the signal that the antenna feeds to the amplifier is the signal received plus the noise received. And why is it important to think about the bandwidth of the receiver? Because as we are going to see later, the noise sources, the thermal noise sources are broadband. And we need to think in a band limited fashion, because if not, we would be talking about infinite power, or at least we would be thinking about a disproportional amount of noise in relation to the real application of the receiver. So this filter here is actually modeling the band pass response of the antenna, the cables, the amplifier and all the receiver chain. Of course, this amplifier here has gain. The goal of the amplifier is to amplify the signal, and it also adds noise. The amplifier also adds its own noise to the signal chain, as you're going to see in just a moment. Let's first think about the problem of amplifying a signal. The signal received by the antenna is very low in power. Let's say it is negative 110 dBm. And of course we placed the amplifier here to amplify the signal, so the next sections of the receiver can use the signal with a higher signal level. In this simple drawing, it becomes very easy to see that if we could create an ideal amplifier that has only gain, we could place here a very large gain amplifier that would generate on the output a signal that is the gain of the amplifier multiplied by the signal received by the antenna plus the noise received by the antenna. And this would be amazing, because any gain we place here, any amount of gain, any number of amplifier chains, any number of amplification devices we placed here would not change the relation between the signal and the noise, because this ideal gain block is amplifying both. We are amplifying the signal and the noise. So the signal to noise ratio, is preserved. This signal to noise ratio here on the output of a perfect amplifier is exactly the same as the input signal to noise ratio. So in this ideal world where we have ideal amplifiers that only amplify the signal, we actually don't have to worry about the signal levels received. Because if the signal here is even lower, like 150 dBm, we could place here an even larger amplifier that would amplify even more. The signal to noise ratio on the output would be the same of the input, and we could follow with our receiver without problem. So of course there is something missing here, and what's missing here is the noise that is added by the amplification step. And this is the problem. This amplification step here, the amplifier itself will degrade the signal, adding its own noise generated internally by the amplificator circuit. A combination of the thermal noise of the active device, all the resistors used in the feedback paths, plus the flicker noise and the shot noise of the active device. So actually, always that we place an amplifier in the chain, we are also adding a noise source that I'm gonna call here the noise of the gain step. So the noise added by the amplifier will add to the signal chain. So actually in the output, we're gonna have here noise of the gain step. It's very clear to see that now the signal to noise ratio is degraded because the signal is amplified, the noise of the input is also amplified, but the amplifier added its own noise here. So this ratio here, the amount of signal in respect to the amount of noise that we have here on the output is lower. And why this ratio is important? Why we talk so much about signal to noise ratio, guys? Because this signal to noise ratio is actually what matters. We saw it here. If we are only thinking about signal level, we could always add an even larger amplifier or more one amplifier to amplify even more to have a larger signal. But of course, this is not the real world. If we look only to the signal amplitude or the signal amplitude in the output of the amplifier, we don't have enough information to know if the receiver will work, because we don't know the condition of the noise. The signal to noise ratio represents exactly what matters. How larger is the signal in respect to the noise? And we can see how much the signal to noise ratio is degraded in each step of the receiver. So we can think about signal to noise ratio as our ability to decode the signal. And what's very interesting, guys, is that for digital telecommunications, for numerical modulations, modern digital modulations, we have very well defined minimum signal to noise ratios that we need to have on the output of the chain so the demodulation step works. So let's say that we are working on a receiver that needs to have a minimum signal to noise ratio here of 10 dB. What a minimum signal to noise ratio here on the output of the receiver chain means? It means that the guys that designed all the rest of the demodulator here, the engineers that designed the modulation scheme, the error correction scheme, all the scramblers, the synchronization codes, all of that, they defined that for all the rest of the demodulator, we need to have a minimum here, a signal power that is 10 times higher than the noise power. This means that ourselves, as the engineers of this front end here, we need to create a topology where we are amplifying the signal without degrading the signal to noise ratio to accomplish this figure here. We need to create a front end that is delivering here a signal power that is at least 10 times higher than the noise power here. Because if we don't do this, all the rest of the demodulator will not work. Now we see that we have a constraint here on the output of the front end, and our job is not so easy, because if we keep placing more amplifiers and more amplifiers here without thinking about the noises added in each process, we're gonna corrupt the signal to noise ratio available on the antenna, and we will not meet the specification needed. And of course, guys, different modulations used here, different forward error correction codes used will change this figure. So we can have receivers that work with a 3 dB signal to noise ratio, a 1.5 dB signal to noise ratio, and it basically changes to the different modulations used, and also very important to the amount of computation and latency that the digital step can take. For example, we are able to create very powerful error correction techniques that work in very large blocks of data to recover signals with a poor signal to noise ratio, but of course we need more compute time and we're gonna add more latency. So actually it's kind of a trade-off. For real-time applications, we cannot create very long and very powerful error correction codes. If it is an offline application, we can have more powerful codes. So it's actually a trade-off of the engineering guys here of the digital world. Well guys, something that is standard is to refer the noise of the amplifier to its input. Here I draw the noise being added inside the amplifier, but actually it's standard to consider that this noise source here of the amplifier is being added here in the input. So this is called the input referred noise. The noise that the amplifier added to the signal chain referred to the input of the amplifier. Now we need to consider that this is what is happening. This now follows a more standard definition of the signal to noise ratio, and the noise is being referred to the input of the devices. Now that we understand the basic picture and the problem of amplification and how amplification comes with its own problems of adding noise to the process, we can understand what a noise temperature means. Why when we talk about noise, we talk about temperature. I will not be entering in the physics here because I don't understand physics, but on electronics we have something called Johnson-Nyquist noise. And it is the noise a resistor produces by the fluctuations of the electron from the thermal activity. I'm not talking only about a physical resistor, a component, but about any material that has a resistivity that defines a resistance over two defined points and that presents itself in a temperature higher than 0 Kelvin. This will generate noise in its terminals in the two well-defined points A and B, and this noise comes from the thermal fluctuation of the electrons inside this material. So any resistance that exists with higher temperature than 0 Kelvin will present noise, self-generated thermal noise in its output. And this resistor can be modeled as a resistor at 0 Kelvin, a resistor that's not generating noise, in series with a noise supply with this amplitude here. This is a very famous formula. 4 times the resistance times the bandwidth. This is why I draw a bandpass filter. We need to think about the bandwidth of the system because this directly defines the amount of thermal noise times the Boltzmann constant times the temperature. A quick pause, guys. If you want to learn more about noise measurements, use the link in the description and take a look on the Keysight use case page about noise measurements. Keysight mastered a lot of different techniques for noise measurement, and they provide a very good application note about this that actually I use it as the reference for this video. So to learn more about noise measurements, use the link in the description and take a look on the Keysight use cases webpage about noise measurement. What's very interesting here, guys, and it makes a lot of sense, is that the available power here is not a function of the resistor, because if we change the resistor we are talking about, we also change the voltage here. So actually the available noise power here, the available thermal noise power here is bandwidth times Boltzmann constant times temperature. This can be easily calculated by calculating available power over this structure here. This makes total sense because the thermal noise is a property of the physics, is a property of the world, is a property of the universe. Thermal noise is not a property of the circuit definition, the resistor, the voltage. And this is actually a power density here because we need to know the bandwidth. As the power noise density is broadband, thermal noise is broadband, we need to know the bandwidth we are working, because if the bandwidth is smaller, the noise we are capturing is lower than if we are working on a higher bandwidth where the observation of the noise power is higher. In a higher bandwidth. And now it will become easier to understand what a noise temperature is. The bandwidth is a function of the system. So we have a system with a modulation bandwidth. We are going to design our receiver front end around that bandwidth. The antenna, the amplifiers, the filtering is around that bandwidth. Boltzmann constant is a definition of the universe. It is a constant. So if the bandwidth of the system is fixed, we have a constant here. Now we can talk about the noise power in terms of the temperature. So now we can talk about what temperature would generate that noise profile. What would be the temperature of this resistor here to generate an amount of power equivalent to the noise power that that amplifier is injecting into the system. And now we can understand this system from the perspective of temperatures. So in the input now we have the power of the signal received and the temperature of the noise. What is the temperature of the noise? Is the Johnson-Nyquist temperature that would generate the same amount of noise that the antenna is receiving. Now the amplifier adds its own noise, the temperature of the gain block. What is the temperature of the gain block? Is the Johnson-Nyquist temperature that would generate the same amount of noise that the amplifier is adding, referred to the input. So we have temperature of the antenna, temperature of the gain block. As all the noise temperatures are referred to the input, the gain of the amplifier will not matter for the SNR calculation, because we have gain on the top and gain on the bottom, because the gain is amplifying all the noise temperature and also the power of the signal. So the signal noise ratio available here now on the output is the power of the signal over the power of the noise. That is a function of the temperatures. And look how simple it is to use temperatures. Noise temperatures will add. It's very easy. If we have more noise sources here, we will add all the noise temperatures of all the sources, and we can easily calculate important figures like the signal to noise ratio using talking about temperatures of noise. This actually simplifies. This is a simplification step, so it becomes easier to calculate and to understand how the system behaves. And of course, we always need to think that we have a fixed bandwidth. So let's think that we are working on a modem, a modulator and demodulator that has a 500 kilohertz bandwidth. So this bandwidth here. So it's really important to always draw the band pass filter that's modeling the band pass response of the signal, because it directly implies in the calculation of the noise. We can design all the system thinking about noise temperatures, and in the end we need to remember to refer these noise temperatures to the correct noise power generated in the bandwidth of the system we are designing. Now we are able to really understand a very interesting aspect about receiver designing. We always read that what matters is the first amplifier of a receiver chain. The first amplifier needs to have low noise figure. We are going to see what is noise figure in the end of the video. But this really means that the first amplifier needs to have low noise temperature. Okay, so I draw here a chain of 3 amplifiers, gain 1, gain 2, and gain 3. Each amplifier is adding its own noise temperature to the signal chain. And look at this is very interesting, guys. Let's calculate, let's draw here the equation that defines the final noise temperature here on the output. As the noise temperatures are all in the linear domain, this becomes very easy to calculate. And remember that we need to calculate the noise temperature related to the input of the amplifier chain. As always, we refer the temperature to the input. So this is a block, an amplifier block, okay? And we want to know the noise temperature of this block. Let's call it TRX. The noise temperature of the first amplifier is already added here on the input. So TRX is the noise of the gain block 1 plus something, plus the noise added by the second gain block. How we are going to refer this noise to the input? We need to remove this amplification step. Do you agree with me? Look at this. As this noise temperature is added here and we need to refer it to the input, if we are referring from the input, it appears here amplified by the gain block 1. So to take from here to here, we need to divide by the gain. Okay, so it becomes T gain 2 divided by gain 1. Look at this. Look at this, guys. And now we need to consider this one here of the gain block 3 divided by the gain 2 divided by the gain 1. Oh, this is beautiful. So now we see that the major contribution for the noise temperature of this block here is the noise temperature of the first amplifier. And this becomes very clear when we think about noise temperatures. The contribution of the second amplifier noise is reduced by the gain of the first amplifier. And this makes a lot of sense because the first amplifier already amplified the signal. And this will add a constant amount of signal. So this constant amount of signal with a larger signal in the input will generate a lower degradation of the signal to noise ratio because the signal is already coming here amplified. Now this amplifier will add a little of noise, but will amplify this all again. Now the signal is very large here on the input of the second amplifier, and it will add a small amount of noise over this very large signal. So here the contribution of the noise temperature to the overall temperature is even lower because the signal is much larger here and the noise is small in comparison to the amplitude of the signal. So the major contribution for noise temperature in a receiver chain is the first amplification step. This is why it's so important to have a low noise amplifier. The first block is responsible for amplifying the signal without degrading too much the signal to noise ratio. All the blocks that follow can have a much looser constraint on the noise temperature because the signal is already amplified and it is larger in comparison to the small amount of noise that is added in each step. This is beautiful. And we need to understand what is important about this video is to understand, now that we understand noise temperatures, is to understand that noise figures have a catch, so we need to think well when we are using noise figures in a design. I will place here the definition of the noise factor. So it is the ambient temperature plus the temperature of noise of the amplifier divided by the ambient temperature, where the ambient temperature is defined as 290 Kelvin. So this looks a bit strange. We are using a defined ambient temperature here to define another factor. But this comes from very old definitions of noise figures. So this is like a memory for 100 years ago. Before we go ahead, the noise figure is the logarithm of the noise factor. I will try to not complicate things here, and you can see that this actually does not make much sense here because actually we have a direct relation. Okay, this is only a transformation, a value transformation from the temperature, the noise temperature of the amplifier. We have a direct relation of any function of noise temperature here to the ambient temperature to generate a noise factor that becomes a noise figure. So you can see that this is actually only a transformation of scales, okay? We are transforming a noise temperature to a different scale of measurement here called noise factor that can be seen as in dB as the noise figure. And why people like to think about noise figures? Let's say this amplifier here has a noise figure of 3 dB. So engineers use the noise figure as a tool to understand something like this. If I have a noise figure of 3 dB, the signal to noise ratio in the input of this amplifier will be degraded by 3 dB. And you remember the importance of the signal to noise ratio we saw in the beginning of the video. So let's think that we have here on the input a signal to noise ratio of 4 dB. If we pass this signal here through this amplifier, the signal to noise ratio here will be 1 dB. So using the noise figure, we can directly calculate the degradation in the signal noise ratio. But this is why I don't like too much noise figures. This only works, and this is important. Look at this. We placed a constant here. This only works if the signal temperature, noise temperature, is also at room temperature. So this calculation implies that this signal to noise ratio was calculated over a signal. We were using antennas, temperature of the antenna. So let's call this the signal to noise ratio of the antenna. This implies that this antenna here has a noise temperature of ambient temperature, okay? So if this is true and you calculate the SNR here with the power of the signal and the temperature of the noise here, and if you use this calculation here, this degradation of signal to noise ratio is right. You can use it. But if the noise temperature here of the antenna is different, and in many occasions it is, like in satellite communications, the noise temperature is much lower here. The antenna looking to the sky has a noise temperature like 20, 15 Kelvin. If the temperature here is different, this calculation cannot be done. So what's the rule of thumb here? Always calculate using noise temperatures. Using noise temperatures, you always will be right. And you saw how it becomes easier to understand the concepts, to understand the need of low noise amplifiers using the concept of noise temperature. Well guys, if you enjoyed this video, please subscribe to the channel and give it a thumbs up. Remember to take a look on the Keysight use case webpage about noise measurements. And I see you in the next video of All Electronics.